So welcome everyone to Informatics Inaugural Lectures. This is the second year we are doing this after the pandemic, and actually it's also the second time we're doing it for informatics. And yeah, we have a backlog and we have many professors. So today you're gonna have two lectures, and one from Yulan and the other from Mohammad Mousavi. And yeah, why we're doing this, right? So because we'd like to celebrate our new professors and new professors at King's. That's the definition that King's uses. So in fact, one of the two has already given one inaugural lecture. So he's an expert in inaugural lectures. But so we expect great things, right? Because you've done it once. But it's really a way of celebrating their career journeys and hopefully to inspire younger people in the room to do great things like Yulan and Mohammed have done. So without further ado, and by the way, I'm Carmine Ventra, I should have said, I'm the head of the Department of Informatics. I'm doing it the wrong way around. And I'm welcoming you on behalf of the whole college. So there couldn't be anyone else tonight. So I'm sorry, guys, but you're stuck with me. So you'll see me often coming back here to introduce and do other things. Okay, so without further ado, I would like to give the floor to Yulan, professor in natural language processing. Yeah, great. So Yulan, the floor is yours.
Thanks, Carmine, for such a kind introduction. So good afternoon, everyone. And welcome to my inaugural lecture on how AI is learning to understand our language. In recent years, we have witnessed the groundbreaking shift in how machines comprehend and interact with human language, largely due to the emergence of large language models and generative AI technologies. So all these technologies, they have revolutionized how we many different things, how we communicate with machines, how we interact with the machines, and how to solve complex problems. And I'm excited to share with you my thoughts on LLMs and also their role in human language understanding. So automated human language understanding can be applied in many different areas. For example, it can help search engines to interpret the user's intent to provide relevant results. It can facilitate translation across between different languages. And it can also be used to power automated customer service through chatbot interactions. And automated human language understanding could also be used in recommender systems to deliver personalized products and services by analyzing users' preferences and also past behaviors. It also plays a key role in question answering systems and intelligence tutoring systems. So let me just start with a brief history of natural language processing, or NLP. So I show a very kind of a brief timeline of research in NLP. Early NLP systems largely focused on machine translation, so that's around 1950s. And approach, they mainly use rule-based systems where linguistic rules were just manually coded into the system. In 1980s, NLP system heavily relied on symbolic AI. And then in 1990s, the rise of the internet provide a massive amount of textual content. So that accelerated the development of corpus-based methodologies or statistical models. And in 2000s, we see largely these machine learning techniques, particularly supervised learning, became the dominant paradigm in NLP. And then in 2010s, the advancement in deep learning radically transformed the natural language processing. So we see the recurrent neural network, particularly long short-term memory networks, improve the sequential data modeling, including speech and also text. And then in 2020s, we saw these pre-trained language models and also the rise of large language models. So this kind of transformation started in 2017. So the transformer architecture was introduced through the groundbreaking paper, Attention is All You Need. And this paper, designed for sequential modeling, relies on the self-attention mechanisms. It revolutionized the way AI processes and also understands human language. And in 2019, Google introduced BERT, built on transformers, so which has shifted basically largely changed the field of NLP. So it introduces a paradigm where the pre-trained language model on some large corpus of unlabeled data can be later fine-tuned to solve some particular downstream task. Following that, a range of different language models built on transformer architecture have been introduced, such as T5, GPT-3, Fluent T5, and Bloom. And in November 2022, OpenAI launched ChatGPT. So it marks the start of a new AI era. So it seems that the LLM becomes so powerful, it can generate coherent, human-like language, and can write code, can also solve very complex problems. And subsequently, numerous LLMs have been released, such as Bard from Google, Llama series from Meta, Claude from Anthropic, and GPT-4 from OpenAI, and more recently GPT-4o and also o1 released from OpenAI. So, so these large language models can actually be easily deployed to develop a range of different applications. So let me just start with some applications powered by LLMs developed in my group. So our first application is a so-called interactive narrative understanding. So in this particular kind of application, we developed this demo system called Narrative Play, which utilizes generative AI to transform storybooks into picture books. So it also enabled the user to actually role play as one of the characters in the book and to have conversations with other characters and creating kind of immersive and personalized experiences. So users begin to upload some story to the system, and GPT 3.5 is then used to extract the main plot. And text-to-image diffusion model is used to create the background image for the story and creating these individual portraits representing the key characters in the story. And afterwards, the users can actually select one of the characters to initiate interaction. So for example, the user can select the character called Charlie Bucket and could start the interaction with the other systems. And so once the character is selected, then all the relevant events involving this character will be presented to the user. So the background will show the location of the event, and event description is narrated at the top. And characters involved in the events appear on the left, and the user selected characters will appear on the right. And then we could have some, kind of pre-attracted conversations played first. And following that, users can engage with other characters. So for example, here, user can actually raise some questions and to ask, things, for example, to Grandpa Joe, right? And then Grandpa Joe would generate a reply. Of course, all this is powered by GPT 3.5. Right, so that's actually, you can imagine, allow the user to continue to interact with the characters and experience the story in a more immersive way. So that's the first application. The second application, we developed a system called Drug Watch. So allow the user to actually search the side effects relating to certain drugs from online medical case reports. So this is actually related to what we call information extraction, or to extract the side effects relating to drugs. We call it adverse drug effect events for pharmacovigilance. So in the example shown here, our system will need to identify the patients or subject mentioned in this medical case report, the treatment she received, and also the effects of this treatment. And we also want to go further, into the details. So in extracting the demographic information relating to this patient, and also the drug names and indication of the treatment from this kind of a treatment subspan. So we developed this system called Drug Watch, and this interface allowed the user to perform the annotation. So we see there's the annotate tab, right? There's also search tab. So the annotation means to extract this so-called abstract effects from the text data and perform the search using this kind of a search tab to search the side effects relating to a particular drug. So for the annotation kind of interface, you can imagine that the user can actually input, write some text to these prompts, and then the user can also choose which language model it want to use to perform this extraction. And then the right-hand side will actually display the results to the user. So in this particular case, the extracted arguments such as age, gender, and drug names and effects will be highlighted. Moreover, the system will actually allow the comparison of the extraction results from different language models. So that's the annotation kind of interface. In the search interface, we allow the user to view the medical case reports relating to certain kind of a drug. So we can see the number of medical case reports reporting the kind of side effects relating to drugs over the year. We can also see a sequence or list of these side effects sorted by their occurrence frequency in histograms and also in the word cloud. And in addition, we will be able, because we perform the search on the PubMed, right? So it's kind of a repository containing all these kind of medical related papers or literature. So we will also be able to retrieve the relevant kind of articles from PubMed and highlight the the relevant information, including the drug names and also the side effects. So that's the second application. In the third application, we actually developed this so-called explainable student answer scoring system for science exams. And this is in collaboration with AQA, which is the largest examination board for GCSEs and A-levels in England. So the scoring of science exams, the problem setup is shown here, right? So given some questions and some key answer elements and also the marking rubrics. So the marking rubric, for example, specified how many points a student answer should get. So for example, if the student answer matches one or two key elements, then the student answer should receive 1 point. Right, so that's the purpose of doing this kind of automated student answer scoring. So we developed this system called Era Chat, and it's an interactive student answer assessment system. So here we actually show there's a list of student answers uploaded to the system. And this is the marking rubric, right? We can also visualize what the question looks like, what's the key answer elements. And then the grading can be performed by different models. So here we actually compare the model generator results by GPT 3.5 and versus GPT 4.0. Of course, you can also use some, like a specifically trained model. And the model could highlight the positive points and negative points from the, the rationales generated to explain the marking decision. So the positive point meaning, the model actually explain why the student answer would be assigned some points, and negative kind of highlights will actually show why there's, there's a mark deducted for the student answer. Right, so apart from this highlighting of positive and negative bits from the rationales generated by the language model or assessors, we can also highlight the student answers where there is a match of some of the key answer elements, right? So the same color, like here, pink color corresponds to the key answer element 7. So that's the kind of key answer element can be found from the student answer. And this interface also allows the user to have a chat with the system, right? So if the users want to actually find out more about the rationale, why the system actually produced this particular rationale, and to do some kind of a counterfactual verification, and then the user will be able to do that through this chat interface. And if the system actually, if we provide the kind of human marking results, or we call it gold standard, right? So the reference kind of labels or reference marks for the student answers to the system, then the system will also be able to generate the evaluation results comparing the performance of different language models in this assessment task. Right, so we have seen, what LLMs can be used to develop a range of different applications, but there are lots of limitations. So I just listed some example limitations here, and you can see this list can actually go on and on. Right? So there are lots of kind of limitations with the LLMs. And next, I will just present some more recent progresses made in my group for addressing some of the LLM limitations. And in particular, we actually explore this so-called LLM self-reflection, and to see, whether the LLM can actually reflect on its previous generator response, critique on its previous action, and then make modifications in order to improve its response in the next round of iteration. So the overall framework looks like this, right? So user feed in some query to the language model. The language model generates some initial response, and this will actually go to some evaluator to evaluate the kind of truthfulness or correctness of the response, and the evaluation results will feed to some kind of reflector, right, to generate the reflection. So pretty much like the teacher, if going to score or to assess the student answer, then the teacher will provide some kind of feedback, right? So this is very similar here. And this feedback can be fed to the LLM generator to refine the response. So you can see like this whole kind of process can go many iterations, right, in order to iteratively improve the system performance. So, so basically, like you can see in the previous example, there would be like 3 LLM cores involved, right? So this generator, evaluator, and reflector. So all these things can be actually performed by LLMs. Now, so we start from the generator. For generator, basically you want to ask the LLM to produce some kind of a response. The simplest way, you just do very simple prompting, right? You just feed in some question to the LLM, ask the LLM to generate a response. Of course, you can do more advanced prompting in this way. You actually ask the LLM to generate some so-called train of thoughts, right? So the LLM explicitly verbalize its thought process before generating the response. Or you can make it more like slightly more complicated or complex, right? So I show one example here. So in trial 1, given some question to the language model will verbalize its initial thought, generate the answer. However, the answer is incorrect, right? And then this feedback will actually like pass back to the LLM. So the LLM would then generate some reflection test. And given this reflection test, LLM will do the second trial run, right? So the same question, and then it now have another kind of a thought generated, and this time it will be able to produce the correct answer. Okay, but in this kind of process, you can see one key kind of a point here is this assessment, right? To assess whether the answer generator is correct or not. And in this kind of this paper, this assessment evaluation is actually given based on the gold standard answer, so it goes based on the true answer. In reality, we know that it's impossible for LM to assess the true answer, right? So how we will be able to address this problem? And I will only highlight the 3 pieces of work, built on this generic framework. So I start from the first work, where we actually use so-called multi-perspective self-reflection for reasoning. So in this case, the search for the solution, we actually use it to encourage diversity. Evaluator is used for the answer or response consistency check. So I will give a more detail here, and this work is led by a postdoc in my group, Han Qi. Right, so basically, first, I think we look into the limitation of LM self-evaluation. As I said before, right, the high-quality external feedback, such as answer correctness, is often unavailable. So for effective self-correction, then we will need to ask the LM to have the ability to judge the correctness of the answers. And this ideally should be performed by LM itself. However, we did some experiments here, right? So we used GPT 3.5 on some QA data sets. So this is a question answering data set relating to STEM subjects, to social science, humanity, and also some other data set. Sorry, other subject areas. And then we compare the kind of iterative prompting the language model to generate the answer, to do the self-reflection and self-refinement, versus if we just give a prompt, we call it auto-stop or never stop, right? So the auto-stop meaning we ask the LM to do the self-evaluation itself, and then based on its own evaluation to decide on how to refine its answer. And never stop meaning like regardless the LLM's generated response, we just tell LM you're wrong, right? You need to refine its previous answer. Now the rationale here is if the LM is very confident about its previous response, then despite this kind of a distractor instruction, the LM should still stick with its original answer. However, as you can see from the figure here, the dashed line is the cases where we actually have the ground truth, right? So we know whether the LM generated answer is wrong or correct, and then we give this signal to the language model. We can see that, of course, like if you have the access to the ground truth, and then through the many iterations, LM would be able to improve its performance. However, with the other two scenarios where we ask the LM to do the self-reflection and self-evaluation, you can see there's no guarantee that with many iterations there will be the improve of the LM performance, right? So our kind of finding here is without the access to the ground truth to validate the LM generated response, there's no guarantee LM performance will be improved through this kind of self-reflection, self-refinement loop. So how should we do that? We actually propose to, rather than just kind of prompt the LM to think about to self-evaluate previous response and then try to do the self-refinement. Now here we actually encourage the LM to think in more diverse way, right? So in a way that we ask the LM to explore more diverse kind of directions or perspectives to solve the problem. And if we have these multiple different directions to solve the problem, we sample one perspective for problem solving, and then we ask the LM to generate response, but also generate the rationale. And this information will fit into some evaluator. And then this evaluator will serve as our reward model. So in this case, the reward will be based on this kind of answer or response consistency across different perspectives. And also for the response consistency, if the LM want to follow one particular path. And the one additional kind of a point we want to consider is the response generated by the LM should be, or the direction generated from the LM should be as diverse as possible, right? So this is kind of like loop in our system. And then we can see some example results here, right? So this is the original question, is the multiple choice question. And that's the initial answer generated by a large language model. And then if we simply ask the language model to self-reflect and self-refine, we can see that the kind of response generator is still incorrect. Now, using our proposed approach, now in this case, we actually try to generate like a multiple kind of a perspective or multiple search directions, right? So the direction for searching for the answer. And then you can see like through some iterations, we will actually, our approach will actually be generated, will be able to produce the correct answer, right? So in this case, our approach will actually based on the response consistency along different kind of search directions, right? So that's the key thing. And then in the second kind of part of work, we actually use the LM to play this game. We call it multi-agent game in murder mystery games. And we can see how these things work, right? So this murder mystery games, usually how that works is a kind of an interactive role-playing game, right? So there are a number of players involved in this game. Each player would be given kind of a story script. And then basically like, each individual will read the script and then do some self-introduction. And then they start to formulate the question to ask some other players, right? And then they could do this, this kind of questioning for 3 or 4 rounds. And then afterwards, each individual will start to kind of do the deductive reasoning to vote for the murderer, right? And at the end, then basically like, either the players identify the kind of particular murderers, or they fail to identify like, murderers successfully. So that's how this game works. And what we propose here is, the original kind of self-reflection, self-refinement framework can actually be formulated in this way, right? So here we have, instead of having human players, we actually have an LLM to role play one of the characters in this kind of murder mystery game. Right, so each language model agent, right, they would provide the kind of self-instruction, and then agents will be initialized with some kind of sensors and memory. So we define some sensors here. Now, these sensors, they are relating to whether the language model agent would be able to identify the murderer, right? So, for example, the language model agent will need to evaluate its emotion towards some kind of a suspect, right? And then whether this suspect has the motive or motivation to commit the crime, and whether this particular kind of suspect has the opportunity to kill the other person, right? And so this search interface here is actually to determine what kind of a question the language model or language agent need to ask, pose the question to some other individual. And then the evaluation here is actually, to kind of like, gather all the relevant information and then to adapt their suspect list, right? So they have some initial kind of list of suspects, but then based on the information gathered, then it will need to do some kind of refinement of the suspects. And then at the end, of course, like the reflection here is the agents need to reflect the values relating to all these sensors based on their received response. So you can see here, the search is actually like relating to what questions should be asked to some other individual. And then evaluation is actually to determine how to kind of, to refine this suspect space. And then the reflection will need to be performed in more structured form, right? So the reflection will need to reflect on these so-called values relating to some particular sensors. And we did some experiments. So this is just to show the performance on different kind of questions relating to character objectives. There's some reasoning kind of questions, and then the relationship among the characters within this kind of story scripts. And we see that our approach actually outperforms some other widely used game playing approaches. And the last bit, we actually like to do this kind of a student answer scoring. So in this student answer scoring, what we did is, we have some example student answers and some human kind of like given labels, right? We need to have a language model to actually to automate this process. But the most important thing is that we need to ask the language model to express or to kind of explicitly state its rationale. So based on the previous framework, what we did is we need to have some kind of imitation, right? We need to imitate the human scoring process by generating this kind of sort tree. And then we need to summarize this sort tree, pass into some rationales. And then using this kind of rationales, we can calibrate the LLM to generate the rationales more faithfully. So give slightly more detail here is actually, the first step, we have some student response. And then, in the past kind of a previous slide, I showed that the scoring need to be performed by compare the student answer with each individual kind of a key answer element, right? And then we can frame this one as kind of binary problem, classification problem, right? So we track whether the student answer contains that specific key answer elements, yes or no. And then we do this repeatedly for all the key answer elements until at the end we reach some kind of decision, right? So given this sort tree, some of the paths leading to the correct scoring decision, some of the paths leading to wrong scoring decision, we can summarize this kind of decision paths and ask kind of rationale. So that gives us kind of a preferred paths or less preferred paths. And we can use this data to do this so-called preference alignment of large language models, and also do some kind of supervised fine-tuning. So that's kind of, the rationale what we want to do here. So again, we can see like our proposed approach basically outperform some other approach. So in example output, actually, like we see the approach actually like, based on this kind of human preference alignment, provide this more succinct information, and then remove all the redundant information compared with the system without this preference alignment. So to wrap up, I think I just only show this one kind of piece of work done in my group, right? So where we built our kind of a different approach on this self-refinement, self-reflection loop. So what's the next? So so the first thing is, we need to have some way to understand the LM of self-reflection. So we still don't fully understand. So why LM self-reflection works or fails in certain cases, and some theoretical studies have explored whether self-correction consistently improve transformer performance, but then we still need a lot of work, more work in this space. Now, on the other hand, I think in terms of reflection strategies, so we could explore using multiple LM to do this so-called hierarchical kind of a reflection, right? Because, for example, we could have a higher level LM handle long-term kind of planning problem, while lower level LM to handle, kind of a more immediate subtask. And we could also have a meta reflection to reflect not just on the individual output, based on but on the LM, the overall reflection process. And of course, we could incorporate the long-term memory into this LM kind of reflection process. Now, another key kind of area is data, right? So we could explore how data should be formulated. So some of the prior work actually incorporate this so-called some special token indicating the reasoning actions, or add some kind of error correction traces in their training data. So this is the equivalent to facilitate explicit learning of planning with the LM. And model architecture, right? So if only certain parts of the transformer architecture or neural network actually require, respond to certain kind of evaluation or critique task, then maybe we should, take this into account to do this dynamic subnetwork activation for task-specific reflection. And finally, I think that's a problem relating to learning algorithms. It might be more effective to focus on so-called learning to self-critique or learning to self-refine, rather than just focus on refinement or evaluating on some specific kind of cases, right? And then given the sort of a vast solution spaces and finding the optimal path based on all these intermediate thoughts can be very slow unless there's some kind of explicit signal to guide the search process. So that's why, whether we could explore some automated approach to actually infer all these unobserved reasoning steps. So I think that's pretty much everything for my talk. And then I will have lots of people to thank, right? So I want to thank my PhD supervisor, Steve Young, and then also my MSc supervisor, John Hui, so for their kind of, invaluable guidance, support, and mentorship throughout my postgraduate studies. And I'm also deeply grateful to all the mentors in different stages of my career for their invaluable insights and advice and encouragement. And I'm grateful to all my collaborators I have had with, with both academic and also industrial collaborators. Of course, I'm grateful to the funding agencies for their generous support for my research. And finally, I would like to thank all my team members, and some of them are sitting here, right? So I have had the privilege to work with so many talented individuals, and whose hard work and also dedication have been invaluable to my research journey so far. And thanks for listening to my talk. Thank you.
Okay, great. Thanks a lot. Okay, so now I'm on the stage to give the vote of thanks. Okay, so clearly the question is, what is vote of thanks, right? And then I went on LLMs and it wrote one for me, so I can give it to you after if you want. But I'll be I'll be a human, and I'll tell you what I think a vote of thanks should be. So we've heard some, what Yulan has worked on in LLMs and the work she's done on both the applications and the limitations. And we can only thank her for the leadership she's showing in the field. And I think we are fortunate to have her here. And actually, I feel reassured that there is someone outside these big corporations who really understand this technology right to its core. And in fact, I have a story to share. So in King's Festival AI 2023, there was a session in one of the rooms upstairs on LLMs. And Yulan was giving the talk, and the room could not be fuller because, of course, it was kind of super popular topic. It still is. What I really, and as you may know, the King's Festival of AI, we open our doors to general public. So there was a lot of general public going in, perhaps worried. By the way, can we substitute ourselves as well? You know, we have LLMs to teach. Can we get them? Okay, thanks. And what I really appreciated was the way Yulan managed to deliver her lecture, her public lecture, in a way that reassured all the people there. And I think you stayed for a long time answering questions of people and reassuring them. So this, I think, summarizes the fantastic work that Yulan is doing. Again, we are very fortunate to have her and all her team here contributing to the knowledge in this. Let's face it, this is the topic of the moment, and it's a defining technology, LLMs, for our future. Okay, so thanks again. All right, now I'm on the stage to introduce our next speaker. I have, as I said, many roles. It's my pleasure to introduce for his second inaugural lecture, I'm joking, Professor Mohammad Mousavi, who's a professor of software engineering at King's.
Welcome, everyone, and thank you for being here so late in the day. I try to keep it lightweight and interactive. I hope you will enjoy it. The topic is also chosen in the same spirit to keep it interactive and lightweight, and I will explain what I mean by spooky actions at a distance in a second. But the more technical topic is about testing quantum software in particular. And don't worry if you don't know what quantum software is, I'll try to explain that in sufficient details. I've organized this talk in 3 parts. The first part starts by giving a very gentle introduction to all the elements that play a role here. I see that it's not perfect. It's different on my screen than here, but never mind. So I will explain what I mean by spooky actions at a distance and give a very gentle introduction to quantum mechanics and the different contributing part that will lead to something called quantum technology and quantum computing in particular. Then I will focus more a bit on the technical parts, apologies, and talk about testing and debugging quantum systems, which is the main thing we are doing at our group at the moment. And then I will talk about the long road ahead of us, which is ongoing research with many people also in this lecture room. So let's start with the spooky actions at a distance. This is inspired by a quote attributed to Einstein. I don't know whether Einstein said that. Probably he did say that. So he didn't like some aspects of quantum mechanics. I mean, he contributed to quantum mechanics significantly, some foundations, but he didn't like some aspects, which I will get to very soon. And he called those aspects spooky actions at a distance. And in fact, he came up with some experiments that would check whether these aspects have any other possible explanation or not. And it turned out that he was wrong. There was no other possible explanation, rational causal explanation for some of those observations, and that led to quantum mechanics. But before we go to those details, let's talk about computing, something that you all know and love. So thanks to Alan Turing and also many others who contributed to the foundations of computing, you know that computing is about calculating using algorithms and bits, right? And I will try to use a running example through my talk. I will use a very simple algorithm that some of you may have seen, but if you haven't seen it, that's fine, especially for younger people in the audience. It's about prime decomposition. So suppose you are given a number, let's say 6, and you want to know what prime factors will be multiplied together to produce 6, right? So given a number, given a positive integer, non-negative integer, or positive integer, we want to find a list of prime numbers such that when you multiply them, you'll get the original number back, right? So if I give you 6, you should give me 2 and 3, right? If I give you 35, you should give me 5 and 7, right? And a very simple algorithm, although this is not the most efficient one, is going to calculate this step by step. It starts from 2 and goes all the way to the square root of n, the number that for which you're seeking prime decomposition. And it will check step by step if n is divisible by f, by the number you're checking. If that is the case, you have already found a factor, right? So what you're going to do is to find the factors of f, because f itself might not be prime, right? And also factors of n divided by f, which will be an integer number, because you know that n is divisible by f, right? So that's an algorithm that could potentially give you, and then you append these two lists together. It will give you back the prime factors of n. Is that so far good? Yeah, good. So and you repeat this until you reach either 1, in which case you return 1, or you reach you reach the fact that n is not divisible by any of these numbers, which means that n itself is a prime number. You report n itself, right? So this is a very inefficient algorithm, and we have come a very long way. This is not my area of expertise, but I know for a fact that we have come a very long way of coming up with much more efficient algorithms to calculate prime factors. But I've taken it upon myself to write it down in Python, and I'm not the best programmer, so here is the Python program that does the job, hopefully. OK, so you start from number 2, right? And then while you haven't reached the square root of n, so that's the f that you saw in my slides, right? While you haven't reached the square root of n, so while f times f is less than or equal to n, you're going to check whether n is divisible by f. If that is the case, then you're going to append the list of prime factors of f as well as n divided by f, right? And otherwise, if n is not divisible, you just increment f by 1 and you iterate until you reach the limit. And let's try that out. For example, on 35, what should it return? 5 and 7. We knew it before, right? So it will give us very quickly 5 and 7, as we expected it, right? Let's try it on another number. So let's try it on 135. I don't know by heart what the answer should be, but it tells me it should be 3, 3, and 5. These are the 3 prime factors of 135. And it's reasonably efficient. So I came up with a number that is like maybe 20, 30 digits. And very quickly you get an answer. So I also wrote another strange number, which is a multiplication of 2 other reasonably small numbers. And I start running this. And it's still running, still running. It will run for the entire period of my talk and much longer. Actually, there are numbers that are not very long, like 200 digits, for which it takes thousands of years before you can calculate their prime numbers, their prime factors. And this has been the basis for an entire field of cryptography. So when you are sending your credit card numbers, for example, on the internet, in order to send it securely, it will use the same scheme. It will use the fact that calculating prime factors of numbers is an inherently difficult problem, to encrypt it and send it over the internet, knowing that if you were to decrypt it, if you were to find the factors, that would take thousands of years before you could find those factors, right? So we can go home and feel safe that prime decomposition is a difficult problem, and hence we can send our sensitive data over the internet, right? Well, one may hope that this is the case. Look, the algorithm is running, and I can leave it on running, and I'm sure that by the end of my talk, you will not have got the answer yet. So the problem is really difficult. However, it turns out that if we take a little bit of distance from Turing and move a few years ahead and use, instead of bits, something called qubits to calculate, the problem suddenly becomes not so difficult. So what are qubits? Qubits are very similar to bits, but instead of being either 0 or 1, which is something we are very used to when we start computing, qubits can take values that are a superposition of 0 and 1. Superposition meaning that it's a combination of 0 and 1, you can think of it, right? So instead of being either 0 or 1, take 0 to be the vector that goes all the way to the top, and 1 the vector that goes all the way to the bottom. It can be any other vector on this sphere, right? That's a qubit. So instead of being either 0 or 1, it can take any value, any combination of zeros and ones over the entire sphere. Even in more complex cases, you can have things that are inside the sphere, but I'm not going to talk about that, okay? So instead of calculating using 0 and 1, you're calculating on something that is a combination of 0 and 1. And that gives you already some level of parallelism because you can calculate for both values, basically, somehow, right? And this is called superposition. Before, when we were calculating on bits, the operations were all local. So if you were modifying a bit, you were sure that the bit next to it is not going to change. However, when you are calculating using qubits, you can prepare them in such a way that they're entangled, such that when you calculate on one, the other one will also change its states automatically, and also at the same time, no matter how far they are. So you can put one in Tokyo, the other one in Los Angeles, and if you modify one over here, instantaneously, the other one will also be modified and will change its states. This is called entanglement, and this is something that Einstein didn't like. That's the spooky actions at a distance. So that also gives you a lot of power for calculations, but also a lot of power for quantum technology otherwise. So beyond quantum computing, there are lots of applications that use this aspect of entanglement. Okay, and the third one is something that can be used to make sure that your information is secure, because you can copy bits and you can steal information from someone else and then store it, say, on a USB stick. But you cannot copy qubits. As soon as you start copying them, you will destroy the original copy. So there is this no cloning theorem or principle that tells you that that you cannot copy information. And as soon as you start peeking into the value of a qubit, it will collapse itself onto one of these bases, for example, 0 and 1. So as soon as you start measuring what the value of your qubit is, it will automatically collapse into 0 or 1, right? The good thing is that the probability of collapsing into 0 or 1 is depending on the state of the qubit. So you can, by doing a lot of measurements, you can reconstruct the value of the qubit, right? But for large systems, you need a lot of measurements to find out what the value of the qubit is. Okay? So these are the main differences between bits and qubits. And that's why using qubits, you can do a lot of new things that you couldn't do with bits. And that's the basis of quantum computing. So let's take an example. The examples will not be as simple. So we are coming about 70, 80 years later after Turing. And this is Peter Shor, who solved the same problem. And the microphone is going on and off. But he solved the same problem of prime decomposition, but this time using qubits. Okay? And the algorithm is slightly more complex, so I can't explain the details in this lecture. It will take maybe a couple of other lectures to go through all the details. But the idea is quite simple. You start from the number you want to decompose, and then you make a random guess. Let's say R. And you calculate the common, the greatest common denominator of N and R. And that's very simple. Euclid already many years ago, many thousand years ago, came up with a very efficient way of calculating that, right? If there is such a greatest common divisor between N and R, then you are done because you have found a factor that is common to N and R. You use that to basically repeat the algorithm that I showed you before, right? You have found a divisor. You calculate the prime decomposition for R, and N divided by R, and you append them together, and you're done, right? However, there is not that much chance that you find that, but there are certain number theoretic properties that allow you to improve your guess. So once you have an initial guess, you can improve your guess by trying many different other possibilities using R, right? So instead of R, you can come up with an R1, R2, R3, R4, R5. And if you try long enough, you're sure that you can hit one such that there is a greatest common divisor, and you can calculate from that point on. The good thing is that all these numbers that you want to try have a very common structure, and you can code them in a qubit by using superposition so that you try them all at once. So instead of trying them one by one, you produce a qubit, you prepare a qubit that is a superposition of all these numbers, and you once calculate it, and with a very high probability, you're going to hit the one that is going to give you the greatest common divisor, right? So this way, Peter Shor was able to solve the problem that was very, very hard, and is probably still running on my laptop in a very short time, and come up with an efficient algorithm of prime decomposition. So your messages are not very safe anymore. Everything that is being communicated on the internet, as soon as we have a good enough quantum computer, we can decompose and read into your sensitive information, including your credit card numbers. Okay, but the good news is that we are not yet there. We are still maybe a few decades from having a strong enough, powerful enough quantum computer that can run this on large enough numbers. But there is hope. Okay, so that was the story of my very short introduction to quantum computing, but there are lots of other applications, many of them happening right now at King's. So people are using it for drug discovery, for virus detection. By virus, I mean real viruses, right? They're using it in neuroimaging, in cancer imaging, lots of applications, but also they're using it in geography, in telecommunication. There are lots of applications of the phenomena I introduced before. They are by no means confined to the area of computing. And that's a very exciting start of a lot of very exciting applications. So what are we doing in this area? We are trying to have a very modest contribution in terms of testing the software that you write for all these systems. So suppose you come up with a quantum algorithm, and quantum algorithms are getting more and more complex. How can we test them? Can we use classical testing techniques to test them? Unfortunately, the answer is no. You can't use usual classical testing techniques for quantum algorithms for many different reasons. The simplest reason is finding out what's going on in a quantum algorithm is a very, very difficult task. And trust me, we sometimes spend hours, weeks, months trying to understand how a quantum algorithm works. And not being a quantum physicist, we are sometimes far from understanding it properly. So program comprehension is a very difficult task, and hence writing tests for quantum programs is a very, very demanding process. So we are trying to attack that problem using different types of possible solutions. The other thing is quantum systems, at least current quantum systems, are very noisy. And the noise is obscuring your view of what's going on in the system. So we need to kind of filter out the noise and tell apart a faulty algorithm from an algorithm that is subject to inherent noise in the quantum system, right? And that's another difficult problem in testing quantum algorithms. It's very difficult to find out whether the issue you're seeing is because of a noise or because of an inherent fault in your quantum algorithm. Entanglement is a big problem. First of all, you need to know where to use entanglements, and also to make sure that the fact that qubits do not remain entangled, sometimes they lose their entanglement, sometimes they become entangled with something outside your system, does not ruin your test results. And most importantly, because you can't peek into the state of your quantum system, you can't do things like breaking and then watching the value of a variable and things like that. Every time you watch a value of a variable, it falls apart. So you need to do you need to develop smart algorithms, smart testing algorithms that do a lot of these measurements, but use them in an intelligent manner to find out what the state of your program is. And given the time, I will be quite quick on what we have been doing so far. So one idea that we have been working on for the past 6-7 years is to develop something called a property-based testing algorithm for quantum systems. So think of prime decomposition. It's difficult to come up with an efficient prime decomposition algorithm, and they can get very complex. However, you know that whatever your algorithm is, when you multiply all the factors, you should get the number back, right? That's a property inherent to prime decomposition. And you can use those properties. You can easily write down properties of your algorithm and then let computer generate tests for you on using those properties. And we have been developing a framework that implements this. So you can write properties of quantum programs, and it will generate tests from those properties, run them, and then check the conditions that you expect from the algorithm. It's slightly more complex because you typically need to do a lot of shots in order to reconstruct the state. and find out whether the condition holds or not. So it's slightly more complex than the old one. I have much more technical slides, but I guess I will have about 5 minutes to conclude, so I will skip through it. So we write properties, and we have now a benchmark of algorithms and their properties. There are data generators that generate qubits that are suitable for testing that property. They will turn into test cases. Then you either simulate it on an actual on a classical computer, or if you are rich, you can even now run it on a quantum computer, right? By the way, there are programming frameworks in which you write your programs, like Qiskit is by IBM, Q# is by Microsoft. There are many others. So you feed your program, you feed your test cases into a simulator or a quantum computer. You gather some test data by doing a few measurements, and then you evaluate that using some statistical testing method. I will skip through the examples given the time, but we have tried it out on a large benchmark of algorithms. We have gathered data about our testing algorithm, about our debugging algorithms, and we are constantly improving them over time. So that's what we have been doing in the past 5 or 6 years about coming up with quantum testing and debugging techniques. And some of the publications are listed here. But there is a lot more to do. So I only presented the testing and debugging frameworks. But for example, to improve program comprehension, we are developing a taxonomy of concepts that are being used very often in developing quantum algorithms. And so far, we have developed a taxonomy of fault types in quantum-specific problems, and we have submitted that for publication. We are working currently on noise-aware testing, various aspects of noise-aware testing, and also we are working on using information theory to characterize how testable a program is and how we can use that to guide test case generation. This is something that we have started very recently. We have a lot of ongoing projects, thanks to funders such as EPSRC and Innovate UK. For example, in this project, we are developing a 3-layered architecture starting from high-level quantum programming concepts, going all the way to the actual realization and verified compilation schemes that make sure that what you have there corresponds to what is going to be run on an actual quantum computer. And we are collaborating with physics, with the condensed matter group at physics to try it out on simulating actual physical phenomena. We have a project with British Telecom where we are evaluating the quality of the software they use on a quantum secure link here in London. And we collaborate with Oxford on a large project for robust and reliable quantum computing. So this is the technical part of the talk. So I walked you very gently through basic quantum mechanics concepts. Then I talked a little bit about what we are doing about testing and debugging quantum systems and also some of the steps ahead. But this is a moment of reflection as well. So I have to thank many people who are involved in this research. In particular, this middle part and also the part ahead of us is done in collaboration with many people. I listed some of them here. So some of them are from our department and my group, but some of them are from similar labs in Norway, some sitting in the audience. We have collaborators at Oxford. We have collaborators at Condensed Matter Group at Physics. Thanks to all of them. Some of them I didn't have photos, so I just listed them without having the photos. But as Carmina said, this is my second inaugural talk, and this is also a moment of reflection about 20-some years of research. So I would like to thank my co-authors through these years. And I spent many hours to collect their... Oh, yeah, by the way, we are running a new institute at NMES. Thanks for the funding from NMES, and I'm thankful to all people who are running this institute together with me. So James Millen is the director. Catherine and Lydia are organizing lots of different aspects of the institute, and people from the support team are looking at industrial collaborations. But as I said, I spent some time gathering the photos of all my collaborators through these years. I didn't find all of them. Probably there are about 20 or 30 missing. But these are 100 co-authors of the papers in the past 20 years. So thanks to all of them. They are reduced to small pictures, but they had big contributions to everything that I've did I've done through these years. And some of them were my mentors, some of them were my teachers, but many of them also influenced my research in a very fundamental way. Thanks to all of them for everything that they did. And also thanks to my family, to my son and daughter, and my wife, Mona, who are in the audience. Thank you all, and thank you for listening. Thanks.
Okay, great. Thanks a lot, Mohammed. Also for you, I have the LLM generated one that I'm gonna give to you. But yeah, so just as before, we talked about the technology that's era defining for the current era. I think Mohammed is working on what is going to define the next year once these machines will be, the quantum machines will be ready. And I have to thank Mohammed for taking leadership and going so much ahead. And I remember when I was a PhD student, I was exposed to qubits and everything, and I said, wow, this is too difficult. So I left it there. But Mohammed is different, right? Mohammed is brave. Mohammed studied how to verify software on normal machines, and then he said, I'm done with that. Let me go to the next challenge. So that's really thank you for the vision and the leadership you showed in your research. I also want to thank you for the mentorship that you do and all the work you do in the department. It's very much appreciated. Okay, so thanks, Mohammed.